Hey guys, Mr. B here. In this video is going to be going over the Chapter 10 review guide. So, here we go. Number 1, a mole of a pure substance contains 6.02 times 10 to the 23rd atoms. This is going to be sometimes true, but not always true. And the reason why it's going to be sometimes true is not all substances are made out of atoms, right? So if it's an element, then yeah, it would be this many atoms. But water is also a pure substance, but water is not made out of atoms, it's made out of molecules. So this is only sometimes true because atoms doesn't apply to all pure substances, it only applies to elements, whereas compounds are also pure substances and they can be molecular or ionic, and they're not made out of atoms. So number 2, the representative particle of a compound is the molecule. That also is sometimes true. If the compound is a molecular compound, then yes, that would be true. But if it is an ionic compound, then no, that would not be true. It would be a formula unit. So, number 3, a mole of CCl4 is composed of 1 atom of carbon and 4 atoms of chlorine. Well, remember that a mole is not the same thing as a molecule, right? A mole is a set number of things. So if you had 1 mole of this material, that would be this many molecules of that thing, and there'd be a lot more than 1 atom of carbon and 4 atoms of chlorine. So this is never true. This maybe is thinking like a molecule of CCl4, but remember that a mole is not short for a molecule. It's a whole different thing, so that's not true. Number 4, a mole of carbon atoms has a mass approximately 3 times as great as the mass of a mole of helium atoms. All right, so basically it's just saying that the mass of a carbon atom has approximately 3 times the mass of helium. So let's see if that's true. In order to answer this question, we're going to want to look on a periodic table. That is not a periodic table, and that's not a periodic table either. All right, give me 1 second to pull my periodic table back up here. Oh, that's why. In a different window. Bam. There we go. Apologize for that. So let's look on our periodic table. Carbon has a mass of 12. Helium has a mass of about 4. So if we took helium and times it by 3, we would get the mass of carbon. And the question was saying that the mass of a carbon atom has about 3 times the mass of a mole of helium, and that would be always true. So that is always true. It doesn't matter if you have a mole of carbon atoms or just 1 carbon atom. It's still going to be a 3-to-1 ratio. So, all right, number 5. The molar mass of nitrogen gas is 14 grams. This is a very tricky one, okay? Now, nitrogen, again, if you look on the periodic table, nitrogen has a molar mass of about 14 grams. But nitrogen gas is not just N, okay? Nitrogen gas is N2 because it is diatomic. It is one of the Brinkelhoffs, which means that nitrogen gas would not just be 1 N, it would be 2 N's, which means it would not be 14 grams, it would be 28 grams, which means that this is not true. Okay, never true. All right, next one, number 6, Avogadro's number. So we're matching here. Avogadro's number is 6.02 times 10 to the 23rd representative particles. That is the definition of a mole. So this is going to be B. Molar mass is, I guess once this is done, can we cross this off? Format, text, strike through. There we go. Bam, that one's done. All right, molar mass. The molar mass would be the mass of 1 mole of anything. So this would be C. Okay, so this one is C. All right. So that one also is gone. A mole is the SI unit that measures the amount of a substance. Now, a mole is also this many particles. Okay, that is true. But since we've already used that for Avogadro's number, the definition for a mole here also is the SI unit for any amount of a material. Okay, so that one is going to be D. And which then leaves us as, for number 9, is A. Representative particles can be atoms, molecules, or ions present in a substance. So that one is going to be A. All right, moving on, number 10. How many moles of PB is 9.3 times 10 to the 15th atoms of PB? All right, so in this one, we are starting with 9.3 times 10 to the 15th. Oh, forgot that we are in Chrome. We gotta do different hotkeys. There we go. All right, let me actually zoom in a little bit on this just because this might be hard to read. There we go. That's probably better. All right, so 9.3 times 10 to the 15th atoms of lead. And they want us to convert this into moles of lead. Okay, so we're going from atoms to moles. The conversion factor we need to use for this is going to be Avogadro's number. So 6.02 times 10 to the 23rd. In this case, atoms of lead is going to be equal to 1 mole of lead. Okay, so here's our conversion factor. And to set this up, we want to cancel out atoms of lead and get into moles of lead. So we're going to multiply this by 1 mole of lead over 6.02 times 10 to the 23rd atoms of lead. And if we do it this way, then our atoms of lead will cancel and we will get into moles. And just to make sure that, again, we understand why we're doing this, I am going to switch over to paper real quick just to show the math workout and make sure that we see that these units are canceling. So we are starting with 9.3 times 10 to the 15th atoms of lead. We are converting into moles of lead. Conversion factor is 6.02 times 10 to the 23rd atoms of lead for every 1 mole of lead. If we set up our conversion table like this, we are trying to cancel out atoms of lead. So on the bottom of our fraction needs to be 6.02 times 10 to the 23rd atoms of lead so that it cancels. And the 1 mole of lead will be on the top. Okay, so we're setting it up like this because we want atoms of lead to cancel with atoms of lead. And then the unit that we have left here is moles of PB, which is exactly what our answer wants. Okay, so we're going to take 9.3 times 10 to the 15th times 1, divide by 6.02 times 10 to the 23rd, or basically just divide by 6.02 times 10 to the 23rd because multiplying by 1 isn't going to do anything. So let me pull up my calculator here. Again, we'll do this in scientific notation. So 9.3 double E to the 15. Okay, so that's 9.3 times 10 to the 15th divided by 6.02 double E 23 equals. All right, so this is a really small number. I'm probably going to want to put this in scientific notation rather than write this whole thing out. And I am going to round to 2 significant figures. So on paper, this is 0. Let's count the zeros here. 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. And then my first 2 sig figs are the 1 and the 5. So in scientific notation, I'm going to move this over 1, 2, 3, 4, 5, 6, 7, 8 places to get 1.5 times 10 to the negative 8th moles of lead. Okay, that is my final answer. 1.5 times 10 to the negative 8th moles of lead. So 1.5 times 10 to the negative 8th moles of lead. That is the answer we're looking for. All right, number 11, what is the molar mass of ethane, C2H6? All right, so to find molar mass, we need to add together the masses of all of the elements in the compound. So that would be 2 carbons and 6 hydrogens. So carbon is 12 grams apiece. We're going to times that by 2. So that's 24 grams from the carbon. Hydrogen is 1 gram apiece. We're going to times that by 6 because there are 6 of them. So it's basically 6 grams from the hydrogens. And then if we add these together, we get that the molar mass of C2H6 is going to be 24 plus 6, which is an easy 30 grams. Okay, so there is our molar mass for ethane. There you go. All right, moving on to number 12. Find the mass of 3.65 times 10 to the negative 2nd moles of K2SO4. All right, so again, we are going to be starting with moles. 3.65 times 10 to the negative second moles of K2SO4. Oh, that's the wrong one. There we go. We want these. And we are converting this into grams because they want us to get a mass. Okay? So if we're going from grams to moles or moles to grams, we're going to need to know what is the molar mass of K2SO4. We're going to have to calculate that. So we're going to have to add together 2 Ks on the periodic table. We're going to have to add together 1 S and 4 oxygens to get this molar mass. All right, so let's take a look at our periodic table because I don't know these ones off the top of my head. So potassium is about 39 grams. Sulfur is about 32 grams, and oxygen is 16 grams. All right, so let's go back to our review guide here, and let's add these in. So this is 39 grams for the potassium, times that by 2, because there are 2 of them. Sulfur is 32 grams, and there's just 1, so we're just going to keep it as 32. And then oxygen is 16 grams, times that by 4, because there are 4 of them. Let's use our calculators here to make sure we get these numbers right. So 39 times 2, so that is 78. That is 78 grams for the potassium. Sulfur is 32, and then 16 times 4 gives us 64 grams for the oxygens. And then we can add all these together. So we get total molar mass is going to be equal to 64 plus 32 plus 78. We get 174 grams per mole. Okay, that is our conversion factor. So we're going to use that to do our math here. We're going to switch over to paper real quick, just so that way we can show the math out. There we go. So switch to our paper. So again, we are starting with 3.65 times 10 to the negative second moles of K2SO4. And we are going to convert this into grams of K2SO4. And the conversion factor is 174 grams of K2SO4 for every 1 mole of K2SO4. Set up our conversion table. Since we're starting with moles of K2SO4, we need to have 1 mole of K2SO4 on the bottom of our fraction so that those cancel, and the 174 grams of K2SO4 on the top. Okay, so moles of K2SO4 will cancel with moles of K2SO4. We're basically going to just take 3.65 times 10 to the negative second and multiply by 174. Again, I will show this on my calculator here. So 3.65 double E negative 2 equals, okay, and the calculator will put it in regular notation, times 174 equals, we get 6.351. We are going to round this to 3 significant figures because of this 3.65 being 3 sig figs. So this would round to 6.35. And this would be how many grams of K2SO4 we are trying to calculate. Okay, so 6.35 grams of K2SO4. So let's go back to our sheet here. And 6.35 grams of K2SO4. That is our final answer. All right. Moving on, here we go. Again, always true, sometimes true, never true. Number 13, 1 mole of any gas occupies 22.4 liters of space. This is sometimes true. And the reason this is sometimes true is because this only works if the gas is at standard temperature and pressure. If it is not at standard temperature and pressure, then 1 mole of any gas could occupy all kinds of different volumes. So this is only sometimes true, okay? Not always true. It has to be at standard temperature and pressure. Number 14, for a substance of known molar mass, the number of moles of a sample can be calculated from the mass of the sample. So this is true, always. If we have a substance and we know the molar mass of it, we can find the number of moles from the mass of the sample just by using the molar mass as a conversion factor. Okay, so this is always true. Number 15, the volume occupied by 1 mole of a gas is dependent on the molar mass of the gas. This is not true at all. The volume of a gas is not dependent at all on its molar mass. The volume of that gas is dependent on if it's at standard temperature and pressure or not. Okay, that's pretty much it. So, number 16, the volume of a gas at SDP can be calculated from the number of molecules of the gas. That is always true. Okay, that is always true. And the reason why that is always true is because if we know how many molecules we have, that tells us how many moles we have. And if it's at standard temperature and pressure, we know that 1 mole of anything is 22.4 liters of space, which is volume. So easily calculated. All right, moving on. Again, some more matching. Number 17, molar mass. I feel like we've already matched this one. This is the mass in grams of 1 mole of a substance. So number 17 is going to be D. We already matched this one up in the first section of the review guide, so that one should be familiar to you. Okay, so that one's gone. Number 18, standard temperature. So standard temperature, remember, is 0 degrees Celsius. So standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure. But standard temperature just in general is going to be C, which is 0 degrees Celsius. Molar volume. Molar volume is 22.4 liters of any gas at standard temperature and pressure. So this is going to be A. Okay, so let's add that one in there. So that is going to be A. Let's cross this off. Standard pressure. So standard temperature and pressure is 0 degrees Celsius and then 1 atmosphere, or 101.3 kilopascals. So this is going to be B. This is standard pressure. Okay, so let's add that one in. And then 21 only leaves one thing left. Molar roadmap is a means of relating mass, number of representative particles, and a gaseous volume of a substance. So 21 is going to be E. That is our molar roadmap. All right, that can be found in the second section of the chapter, 10.2. So if you're looking for the molar roadmap, that's where you'll find it. All right, let's take a look at question number 22. What is the density of N2O gas at STP? All right, so this one can be a little bit tricky because there's no numbers. So you might be thinking to yourself, like, what am I even supposed to do here? Well, they want us to find a density. So density is typically given in grams per liter, okay? And they're not giving us any numbers to begin with. However, they are giving us a chemical formula, and we can calculate molar mass of any material from a chemical formula. So what we can do is we can first find the molar mass of N2O, which is in grams per mole, and then convert that into grams per liter. And really, if we look at it, we're really just converting moles into liters because both of these have grams in them. So we don't need to convert or change the units of grams. We're just changing moles to liters. Okay. So first things first is let's find the molar mass of N2O. So to do that, we're going to need to add together two N's and one O. Now, we've already seen this a lot. So we should know by now that nitrogen has a molar mass of 14 grams. So that's 28 grams for the N's. And oxygen has a molar mass of 16 grams, and there's just one of them. So total molar mass of N2O is going to be 28 plus 16. So let's add these together in our calculator, again, to make sure we don't get this incorrect. So this is 44 grams per mole. So that's what this first number is we're starting with, 44 grams per mole. And we're going to convert this into grams per liter. So basically, we're just converting moles into liters. And since this gas is at STP, we can use molar volume to do that, okay? So molar volume is 22.4 liters per mole. And that's a conversion factor we can use to cancel out units of moles and get into units of liters. So let's real quick switch over to our paper so that we can see this worked out better. Okay, so we have 44 grams per 1 mole of N2O. Okay, and I'm writing it out here as a fraction. This is our molar mass. It is consisting of 2 units. And we are going to convert this into a density, which is grams over liters. But again, we're pretty much just converting moles into liters because the grams we don't want to change. We are going to use molar volume to do this. So 22.4 liters of N2O for every 1 mole of N2O. If we set up our conversion table, we're pretty much just going to convert moles into liters. Okay, so we're going to use this conversion factor. Since we have moles of N2O down here, we want to put moles of N2O up here so that those cancel with each other. And 22.4 liters of N2O on the bottom of our fraction. So moles will cancel, okay, because they're opposites from each other. And then the units that we have left that we have not canceled out yet are grams over liters, which is exactly what our answer wants as a density. So we're going to take 44 grams times 1, divide by 1, divide by 22.4. Or if you want, we can just take 44, divide by 22.4, because timesing by 1 and dividing by 1 isn't going to do anything. Okay, so let's do this on our calculator here. So 44 times 1, divide by 1, divide by 22.4 equals, and we got a lot of different numbers here, 1.9642, whatever, but we are just going to round this to two significant figures because well, actually, it doesn't really matter. This molar mass that we calculated as a whole number, we could have made it more precise. So let's just keep it as 1.96. That's completely fine. So our density here is going to be 1.96 grams per liter. That is our density. All right, so let's shift back to our review guide here, and we are going to get 1.96 grams per liter as our density for N2O. All right, moving on to problem number 23. What is the mass of 2 moles of NaCl? So in this problem, they're telling us that we have 2 moles of NaCl, and they want us to convert this into grams of NaCl because they're asking for a mass. If we're going from moles to grams, we're going to need to know molar mass. So we'll have to calculate this from the periodic table. So the mass of sodium, the mass of chlorine. So let's go real quick look at our periodic table. Sodium has a mass of about 23, so 22.9, we'll just say it's 23. Chlorine is 35.453. If it's in the middle like this, like 35.5, we don't really want to round up to 36 or round down to 35. So I'm just going to keep this as 35.5. So let's go back to our review guide. Let's add these in. So sodium had a mass of 23 grams. Chlorine was 35.5 grams. Right, so let's add these together. So we get a total molar mass of 23 plus 35.5. So this is going to be 58.5 grams per mole. That's our conversion factor. We're going to need to use that to do our math here. So let's switch over to our paper so that we can see the math work. So we are going to be starting with 2 moles of NaCl. We're going to be converting this into grams of NaCl. And the conversion factor we are going to use is molar mass, so 58.5 grams of NaCl for every 1 mole of NaCl. Right, so there's our conversion factor. Let's set up our conversion table. And since we're starting with 2 moles of NaCl on the top of our fraction, for our conversion factor, we want to put the 1 mole of NaCl on the bottom so that it cancels out. The 58.5 grams of NaCl will be on the top. Again, we see that moles of NaCl will cancel. And then math-wise, we're going to take 2 times 58.5, divide that by 1. That will get us an answer in grams. So let's do this real quick on a calculator. So 58.5 times that by 2, and we get 117 grams of NaCl. Okay? So this is our final answer we are looking for, 117 grams of NaCl. So let's switch back here to our review guide and let's add this in. So our final answer is 117 grams of NaCl. All right, that problem is done. Moving on to problem number 24. How many moles are in 16 grams of O2? All right, so again, we are starting with 16 grams of O2, and we are going to be converting this into moles of O2. So just like in the previous ones, we're going from grams to moles or moles to grams. We're going to need to know molar mass to do this problem. So let's find our molar mass here. We have 2 oxygens, and on the periodic table, oxygen has a mass of 16 grams. We're going to times that by 2 because there are 2 of them here. So the molar mass is going to be 32 grams per mole. So once we have that, that is our conversion factor. And then we just need to do the math and set up our conversion to make sure that we cancel out grams and get into moles. And we got a new piece of paper here for us so we can do some math work. Again, let's switch over to our paper. So we are going to be starting with 16 grams of O2, and we're converting this into moles of O2. Our conversion factor is 32 grams of O2 for every 1 mole of O2. Set up our conversion table. Since we're starting with grams of O2, the 32 grams of O2 in our molar mass needs to go on the bottom of our fraction, so that cancels. The 1 mole of O2 is going to go on the top of our fraction, so we don't cancel out moles. So again, we see grams of O2 and grams of O2 canceling. Mathematically, we're going to take 16 times 1, divide by 32, or just simply take 16 divided by 32. 16 divided by 32. We get 0.5. And just to make it two significant figures, I guess we'll go 0.50. So 0.50 moles of O2, that is our answer that we are looking for. So again, let's go back to our review guide. Let's add that in. So 0.50 moles of O2 is our answer that we are looking for. All right, almost done here. 10.3, true or false? It is necessary to know the formula of a compound in order to calculate its percent composition. Yeah. If you don't know the chemical formula, you can't find its percent composition because you're trying to find the percentage of all the elements in it and then break that down. If you don't have that, you can't find it. So, yep, that is always true. Number 26, if the percent by mass of carbon in methane is 75%, then 100 grams of methane contain 25 grams of nitrogen. So, if the percent by mass of carbon in this is 75% carbon, then that means 25% of it would be hydrogen. So in 100 grams, 25 grams would be hydrogen because 25% of 100 is 25. So yes, this is always true. All right. Number 27 and 28, we're actually going to get rid of because we are not doing anything with empirical formula or molecular formula. That also goes for this as well. So we're going to delete those. All right, well, that pretty much makes that problem easy. So percent composition is A. Describes the actual number of atoms of each element in a molecule of a compound. All right, there we go. Oh, I'm sorry. Hold on a second. I realized I deleted the other choices. We don't want to delete those. So let's do this. Percent composition is the percent by mass of each element in a compound. So this is C. I apologize. That is C. But we're not going to be answering these two. So we'll just disregard 30 and 31. Okay. So my bad. There we go. So let's just cross that one off. So we know that 29 is C. And then we're not doing empirical or molecular formula. So we'll just ignore those two. All right. Moving on to the last problems here. This one is solve the following problems in the space provided. Show your work. What is the percent composition of each of the following? So we need to find the percent composition of each of these. To do that, we're going to need to know the molar mass of each one, the mass of each individual element to make up that molar mass, and then we can find our percentages. All right, so for the first one, we need to know the mass of 2 chromiums. We need to know the mass of 3 oxygens, and then we need to know the total molar mass of this compound by adding those together. All right, so let's go look on the periodic table. I don't know these off the top of my head. So for chromium has a mass of about 52, okay, 51.99. We'll just say 52 for chromium, and oxygen is about 16. So on our review guide here, chromium is 52 grams, times that by 2, because there are 2 of them. Oxygen is 16 grams, times that by 3, because there are 3. So let's do this math out real quick on a calculator. 52 times that by 2. That gives us 104 grams for the chromium. And 16 times 3, that gives us 48 grams for the oxygens. And then if we add those together, we get a total molar mass of 152 grams. So then to find our percentages, we know that the percent for chromium, nope, that's not a percent sign. There you go. Percent for chromium is going to be the mass of the chromium, which is 104 grams, divided by the total mass of the whole compound, and then times that by 100 to get a percentage. So 104 divided by 152 times 100. And I guess we'll just round to whole numbers to make it easy. So this is going to be 68% for chromium. So there's 1 percentage. Oh, there is 1 percentage right there. And then we could take 100 minus 68 to find the oxygen, but we're just going to do the math out for that one too, since we happen to know the numbers. So percent for oxygen is going to be the mass of the oxygen, which is 48 grams, divide by 152 grams, and then again times up by 100. So let's do this out again. 48 divide by 152 times 100. And again, to round to whole numbers, to make this equal to 100%, you get 32% for the oxygens. All right, so there is that one. We're going to do the same thing over here for the HGS. We need to find the mass of mercury. We need to find the mass of 1 sulfur. And then we need to get the total molar mass for HGS. And then we can do our percentages. All right, so again, we'll need to use a periodic table here. I don't know these off the top of my head, or at least not for the mercury, I don't. Mercury is here, so 200.59. So we don't really probably want to round that up to 201, and we don't want to round down. So we'll just say 200. We'll just say 200.6. Okay, and then the sulfur is basically 32. So mercury is 200.6. So 200.6 grams. Sulfur is basically 32 grams. So let's add these together. So 200.6 plus 32. So we get 232.6 grams for our total molar mass. So for percentages, percent of Hg is going to be the mass of mercury, which is 200.6 grams, divide by the total mass, 232.6, times 100 equals. All right, so 200.6 divided by 232.6 times 100. Again, let's just round to whole numbers and make it easy. 86% for mercury. And then for oxygen, or sorry, for the sulfur in this case, we are going to take 32 grams, divide that by 232.6 grams, and then times that by 100 to get that percentage. So 32 divided by 232.6 times 100. Again, rounding to whole numbers, we'll get 14% for the sulfur. All right, 2 left to go. We got to do it like this. Here we go. Okay. So for this one, it's a little bit trickier to find molar mass because we have these parentheses. So remember that this 2 multiplies everything in the parentheses. So we are adding together all of the elements here. We're going to have 2 nitrogens. We're going to have 8 hydrogens. And then 1 sulfur. Okay. So remember that this 2 multiplies everything in the parentheses. It doesn't multiply things outside the parentheses. So 2 N's, 8 H's, 1 S. All right. Now, I don't need to use the periodic table for nitrogen. If you have to, go look at it. But nitrogen is 14 grams. We'll times that by 2 because there are 2 of them. Hydrogen is 1 gram apiece. We'll times it by 8 because there are 8 of them. So that's 8 grams. And then sulfur, we just looked up on the periodic table for the last one. That's just 32. So our total molar mass is going to be equal to 28 grams plus 8 grams plus 32 grams. This gives us 68 grams total. So then for our percentages, we have percent N, we have percent H, and we have percent S. And we are going to take each individual element mass and then divide that from the total. So 28 grams for the nitrogen, divide that by 68 grams for the compound, times that by 100 to get a percentage. So 28 divided by 68 times 100. Again, we'll just round to whole numbers, keep it easy. So this is going to be 41% for the nitrogen. For the hydrogen, we'll take 8 grams divided by 68 grams, and then times that by 100. So 8 divided by 68 times 100. Again, rounding to whole numbers, this is going to be 12% for hydrogen. And then the last one here for sulfur, we'll take 32 grams, divide by 68 grams, and then times it by 100 to get its percentage. So 32 divided by 68 times 100. Again, rounding to whole numbers, we get 47% for the sulfur. And just to double check, if we add all these together, so 41 plus 12 plus 47, we get exactly 100%. Which is exactly what should be working out. So these percentages look good. All right, last one over here we have is Al2 So4 3. Again, we need to find the molar mass. We have some parentheses and stuff. First though, for aluminum, we have 2 of them. Okay, this 3 here is going to multiply things in the parentheses, but it doesn't multiply things outside the parentheses. So it does not apply to the aluminum. So we have 2 aluminums. This 3 is going to multiply the sulfur. So we have 3 sulfurs. And it is also going to multiply to the oxygen. So 3 times 4 gives us 12 oxygens. Okay? All right, so now I am going to have to go look on the periodic table for this one because I don't know these numbers off the top of my head. So for aluminum, aluminum is 26.9, so let's just say that's about 27. Sulfur is 32, and oxygen is 16. So aluminum is 27. So again, let's go back to our review guide here. So aluminum is 27 grams, times that by 2. Sulfur is 32 grams, times that by 3. And oxygen is 16 grams, times that by 12. All right, so let's do some math out here on the calculator. So 27 times 2. This gives us 54 grams. Uh-oh, what just happened? Let's undo what I just did there. So this is 54 grams for the aluminum. 32 times 3. So that is 96 grams for the sulfur. And then lastly, 16 times 12. That is 192 grams for the oxygen. All right. So again, let's get our total molar mass. We got to add all these together. So 192 plus 96 plus 54. So this is a pretty big compound. 342 grams for the total. And then lastly, to find our percentages, percent for aluminum is going to be the mass of the aluminum, which was 54 grams. Divide that by the total, 342 grams, times that by 100 to get its percentage. So 54 divided by 342 times 100. Again, let's round to whole numbers to keep it easy. So it's going to be 16% for the aluminum. For the percent sulfur, this will be 96 grams divided by 342 grams, and then times it by 100 to get that percentage. So 96 divided by 342 times 100. Again, let's round to whole numbers to keep it easy. So 28% for the sulfur. And then the last one here is the oxygen. So this is going to be 192 grams divided by 342 grams, times it by 100 to finally get that percentage. And that's probably going to be the largest of all 3 percentages because it's 192 grams out of 342. So it is by far the most of all of them. And we get, again, whole numbers here, 56% for oxygen. And again, just to double check to make sure that these add up properly, let's add 56 plus 28 plus 16. We get exactly 100%, which is what we should have. So, all right, that is all the problems for the review guide here. If you struggle with any of those, or if any of those didn't make sense, by all means, please feel free to email me so that I can help you out. I have no problem doing so. All right, guys, that's it. Good luck with your test, and I will see you in the next chapter.